Hey everybody, welcome to the next Timescale Twitch stream. My name is Attila Toth, and this is the third episode of the Stocks and Crypto SQL Show, which is about trying to help the community working with stocks and crypto data inside TimescaleDB with SQL and anything that could help the community working with these two data types. So today's episode will be about building fast dashboards, and I'm going to be focusing more on the database side of things and less on the dashboard side of things. But yeah, let me share my screen. We are live, by the way, on YouTube and Twitch. I'm trying to look at the comments while streaming, so if you have questions or comments, let me know. And so, as I said, we are going to focus on two things. So first, I'm going to show you a simple process that you can replicate yourself to build fast dashboards. And then I will also show you how you can basically compress the data that is displayed on your dashboards, and thus reducing the storage costs with TimescaleDB. If you're watching the recording, because we post these live streams on YouTube as well, so if you're watching the recording, there are links in the description, things like timestamps, so you can skip to the part that you like, and also there will be other useful resources in the description. Alrighty, so just a quick agenda. So first, I will talk just briefly about continuous aggregates because we have a lot of content about continuous aggregates on our YouTube channel. And I will talk more about how continuous aggregates can help you basically create fast dashboards and how they can work well together, dashboards and continuous aggregates. Then we will actually create a real dashboard from scratch. We're going to be using Apache Superset as an example, but you could use any other dashboarding tool. This stream or the content I'm going to show you should be helpful to you either ways. Then in the third section, I'm going to demo compression on a real data set. And because this is the Stocks and Crypto Show, I'm going to be using an NFT transaction data set to try compression on. And then finally, I will show you some next steps and how you can learn more, or how you can move forward if you want to, if you would like to learn more. Alrighty, so continuous aggregates to fuel dashboards. So just a quick reminder, what is continuous aggregates? Again, we have a lot of content about continuous aggregates on the YouTube channel. Actually, as I remember, I used and demoed continuous aggregates last week during our stream. So check those out. But continuous aggregates is basically materialized view optimized for time series data with continuous and incremental refresh and faster aggregate queries. So basically, a continuous aggregate is very similar to Postgres materialized view, except that it has a much more efficient way to refresh data. So instead of basically dropping the view and recreating the whole materialized view from scratch every time there is new data, continuous aggregate only refreshes that part of the data that you specify, because you need to specify time interval. And so this way, only data that has actually changed will be updated in the materialized view. And obviously, because we are talking about a materialized view and the aggregated values are stored in the materialized view, the queries will be much, much faster. All right, so that's about continuous aggregates. Now let's see why a continuous aggregate would be useful for dashboards specifically. So one of the interesting features that TimescaleDB continuous aggregates has is what we call real-time aggregates, which basically allows you to fetch data from the database, from specifically the continuous aggregates, even before materialization. So let's say you have a continuous aggregate that gets refreshed, maybe every day or every week, or whatever requirement you have. But you also have data constantly coming in, and new data is actually not materialized yet. So if your dashboards rely on the materialized view, and it's just a regular Postgres materialized view, then the dashboard will not have the up-to-date information, the up-to-date data. With continuous aggregates, the dashboard will have the up-to-date information always, because continuous aggregate can get the portion that is materialized already. Continuous aggregates will return the data from the materialized view, the materialized table, and data that is not yet materialized will be returned from the actual underlying table. So this way, everything, all the data that is there in the database will be shown on your dashboard. Then, as I said, continuous aggregates help you to create fast queries. And obviously, fast queries will help creating fast loading dashboards. Usually, I mean, I'm not saying usually, but probably if you have a slow dashboard that loads charts slowly, probably you have some query performance issue. You have not so well optimized queries. And so continuous aggregate can help make those queries faster. But also in some cases, you might have some issues on the front end. Maybe it's the dashboard has some bugs or something that slows the loading down. So that might be a problem as well. Then another thing continuous aggregates allows you to do is easy and fast filtering on the dashboard side. So in your actual dashboarding tool. This is because, as I said, continuous aggregates is basically materialized view. So everything is, not everything. In case of real-time aggregates, some data might come from the actual underlying table. But let's assume that most of the data come from the actual materialized table. And in that case, that's going to be, pretty fast. And then you can use the dashboard to further filter on the result of that query. And you can also use, if your dashboarding tool supports SQL, you can also use where clauses or any SQL command or function inside your dashboard tool. Another interesting feature is that while the view is getting refreshed, your dashboard will keep working as usual. And this is because, as I said, as opposed to regular Postgres materialized views, continuous aggregates don't recreate the whole table from the whole materialized view from scratch. They just update the most recent part or the time period that you specify to be updated or to get updated. And so while the continuous aggregates is getting refreshed right now, your dashboard will work properly. There shouldn't be any problem. And then I might have mentioned this, but because of this whole process or the way how continuous aggregates work, the refresh process is much faster. Data gets updated much faster because there is less data to be updated. I think that's it. And yeah, just as a summary, so basically, continuous aggregates help you, achieve good query performance, and good query performance can lead to, fast dashboards. All right, now let's do some demo. Again, this is going to be exciting because there are quite a few things that could go wrong here because I'm using a local Superset instance and other things. But let's create a real continuous aggregate that we will later use for the dashboard, to create a dashboard from scratch. All right, so let me jump to dbeaver. I hope you can see that. So, well, actually, I have a slide, as I remember, to show the materials view or the contents aggregate. So this is the contents aggregate that we are going to create. This is very similar to the one that we created in the previous stream. You can find the recording on YouTube. This one is using the NFT sales data set that the Timescale NFT starter kit has. Again, if you have not heard about that, links will be in the description, or you can just probably Google Timescale NFT starter kit, and you will find the GitHub repository and the tutorial and everything else. All right, so we are going to create this contents aggregate. I'm going to call it demo collections daily, because this will basically aggregate collections in 1 day buckets. So we have the collection ID, first of all, which is the unique identifier of a given NFT collection. Then we create the time bucket. We specify 1 day as the time interval. We call it bucket. And then we have different aggregate queries: count, sum, max, mean, average. This is probably similar to what you would do if you store stock prices or cryptocurrency prices, or in our case NFT sales and NFT prices, because the total price field contains the price of the NFT, and we are calculating the count star. We are calculating the volume, which is basically the trading volume in that day for the given collection, and then we have the sum of the total price, which will give us the volume in Ether. Ether being the cryptocurrency used to buy NFTs. Then we have max total price, which will return the maximum price paid for the given NFT. Similarly, we have min, which will return the minimum price paid for the NFT. And then we have average, obviously the average price paid for an NFT in the given collection on the given day. And yes, we have a where clause to only show results that used Ether as the cryptocurrency, and we are grouping by the bucket and collection ID. All right, so this is the definition of our contents aggregate. Let's actually create this. So first of all, let's make sure that I don't have a contents aggregate with the same name, just to make sure. So there is no with the same name. That's great. Now let's create this contents aggregate that I just showed you. So if I start running this query, as you can see here, you were able to see, but so it basically materialized everything that we currently have in the table, and it created a contents aggregate called demo collections daily. Now let's see what's actually inside this contents aggregate. So if I run this query, you can see that we have, as we defined when we created the contents aggregate, we have collection ID on the left, we have bucket, we have volume in Ether, max price, min price, and average price. So this will serve as the foundation for the dashboard that we will create. And as you can see, there are quite a few different charts that you could create using just this contents aggregate. You could create a time series chart using the volume to see the volume of one collection over time. You can create a very similar time series chart using the Ether volume column, and we also have max price, min price, and average price. All right, so now that we have this ready. On the database side, we are good for now, and it's time to create a dashboard. And to create the dashboard, I'm going to be using, as I said, I'm going to be using Apache Superset, which is I'm not going to go deep into like what Superset is, but basically it's an open source data exploration tool, and it works well with TimescaleDB because it works well with any database that basically speaks SQL. Um, and hopefully in the future we will be able to delve deeper into Superset and how to use TimescaleDB and Superset together. But that's for some future stream. All right, so I have a local Superset instance running, which is at the moment it's not very exciting. It's just a very empty dashboard that I created. It's called demo dashboard. I have a collection filter here, which is going to be used to filter collections, but currently we have nothing to filter. That's why we created the continuous aggregate. So what I'm going to do now is we need to somehow connect the continuous aggregate that we just created here. So this continuous aggregate, we need to connect this to Superset. The way to do that is, again, it will depend how to do this. It will depend on the dashboarding tool you use. Currently I use Superset. So I will need to go here, datasets. I have a bunch of datasets here. And I will probably just remove this one because I'm not sure what it is. But I will create a new data set. I will create the database that I'm using. I will need to select the schema, which is public. And here, Superset says table, but actually, Superset considers a table, everything, including a table, a view, or a materialized view as well. So if we go here, this is what we're looking for, demo collections daily, because this is the name of our continuous aggregates. So I'm choosing this. I will click add. Now it will think for a couple of seconds before telling me that the data set has been added. Hopefully. Yes. So data set has been, the data set have been saved. So right now, what we can do, we can go back to our dashboard, which is demo dashboard. And now the filter might work, but I will show you how to configure this. So in newer versions of Superset, there is a better way to apply filters. This is not the newest version of Superset I'm using on my local machine, but this is very similar. So basically, I will need to change the data set that the filter uses. And now I have demo collections daily, which is the continuous aggregate that we need. So I will click that, proceed. And now I have, you might be able to see it on the left. I see all the columns in Superset that, the continuous aggregate has, which means that if I want to create a new filter, I just go here, filters. I click the pencil icon, and in the columns, I see all the columns that the continuous aggregate has, and I can set which column I want to choose to, for filtering. And here we want to choose a column which is a unique, which is unique, which serves as a unique identifier for the collection, which is obviously the collection ID. So I'm going to choose that, and I'm going to label it collection ID. And default, I don't know. Let's have a default something. I don't know, 600. Let's see if there's a collection ID 600. I don't know. So I created the filter, Now I just need to save it and add it to the demo dashboard, and save and go to dashboard. So if I go here, it will think for a couple of seconds. And as you can see, there is already a collection ID, which I defined to be 600 by default. But if I click here, it's a drop down, a very long drop down with all the collection IDs that is available in the database. So we can choose, any collection ID. So that's going to be our filter for now. We will change it later because collection ID is not really user friendly. Like, we don't know what this collection ID actually refers to. But for now, let's just stay with this. Now we are going to create a time series chart using the continuous aggregate. So to do that, we can go here, charts. I go create a new chart. We need to choose the data set. Again, we are using the continuous aggregate, which I hope I will be able to find. Here it is, public demo collections daily. So I choose the data set, and then I will find my favorite time series chart, which is the time series smooth line. I don't know, that's my favorite time series chart, but there are other different time series charts here. I choose this one, create new chart. So this will do nothing for now. We need to configure it. So first of all, we can set the time column, the time grain. That's not really useful for us now because we don't want to change that. So let's just go with original value. What is important is the query part in Superset, where the metric. So the metric, if we go here, we can select the column that we want to use from a drop down. As you can see, again, these are the columns that we defined in the continuous aggregate. And the metric will be used to actually create the points on the time series chart. And so we need to decide what we want to show. For now, let's go with volume, which will show the trade volume of the given collection on the given day. So I choose this. Now we also need to, we cannot click save for now. We also need to define an aggregate function here, but this is actually not like, it wouldn't be needed technically because we already created the aggregated value. So the continuous aggregate stores the aggregated value. We don't need to further aggregate it, like it's already done. But because this dashboarding tool works this way, we need to define something. So I usually use max because that's not going to change the value of the aggregation. Just you can use average, min, or sum as well. Just don't use count. Don't oops yeah, I'm not gonna be able to draw, but don't use the count or count this thing because that's not going to work. Use average, max, min, or sum, because Superset will also group by collection ID, but we already know that we only have one item per collection, one row per collection. So let's go with max, and let's call it trading volume of the collection. All right, save. Now we also need to specify a group by column. This is important because this is what Superset will use to actually create the chart. So here we need to choose the collection ID. So we choose the collection ID, and that should be it. So I hit save. And let's give it a name. Let's call it trading volume. Let's save it and go to the dashboard. So what we see here is that we have the collection filter, which is by default 600. So that's going to be used to try to filter on the continuous aggregate. Let's try a different. Let's try to find an ID that actually exists, because based on the chart, we don't have a value with 600. So let me quickly find the ID of the 𝗥𝗲𝗃𝗁𝗃 collection, which is a popular collection. I go. I think it's called 𝗥𝗲𝗃𝗁𝗃. If I where if I run this query, yes, this will return a row which represents the 𝗥𝗲𝗃𝗁𝗃 collection, and it has an ID of 203. So I'm just going to copy this, go back to the Superset dashboard, put the ID here, and click apply, and the chart should update. And there you go. So we created this. Maybe I can even enlarge it. All right. So we just created this time series chart, and this is using the continuous aggregate. I will just delete this that we created here. So this is the continuous aggregate. This is the time chart, and it uses the filter that is defined here on the top left. And if we hover, we can see the specific data points. And as you can see, we have quite a lot of data from the past. We have data going back, January, or even the last day of last year. So this is done. Now, one thing which I mentioned, which is not really user-friendly, is the collection ID filter. So a better dashboard would be if we can filter based on a unique identifier that is actually meaningful, or at least more meaningful than an ID. And luckily, if we go back here, I shouldn't have deleted that query, so I just Control Z. So we have the collections table, which includes a lot of collections. And as you can see here, let me make it bigger a little bit. As you can see here, we have ID, we have slug, we have name, we have URL, and we have other things. But just one other thing, the details, 𝗔𝗯𝗃 column. But here, the important thing is that there are actually two unique identifiers in a row. One is the ID, but the other one is slug. So slug is also a unique identifier, and we can use that to filter on the continuous aggregate. Now, there's a problem, which is in the continuous aggregate definition, we don't have the slug. We have collection ID because the collection ID column is part of the NFT sales demo 2 table, which includes the transactions, the time series data. But that table doesn't have the slug. So how can we solve that? We can join the continuous aggregate because, again, that behaves like a regular materialized view in Postgres. So we can join that continuous aggregate with the collections table, and that way we can get to the slug, which is pretty much what happens with this query, or what this query does. So this query will join the collections table with the continuous aggregate, and it will choose all the columns from the CAG, aka the continuous aggregate, and additionally the slug column from the collection. So if I run this query just to see how it works, it returns the continuous aggregate columns with all the rows, plus the slug at the beginning, which is crucial for us because we need the slug column for the dashboard, so we can the filter functionality can be more useful. So we have created this. We can create a query like this, but how do we actually get this into the dashboard so the dashboard will actually make this query? So there are multiple ways you can do that. This is one way, which is to create a view, not a materials view, just a regular view in your database, specifically for Superset to use. In this case, I call it demo collections daily view. And what this view will do is, pretty much what I showed you. It will give everything from the collection, the continuous aggregate plus the slug. And I also added one additional where clause just to show you that this is something that you might find useful in your case if you build dashboards. Is that you can filter, because we are using time series data, and so we have data going back, as you can see here, even the last day of last year. So you might want to use some kind of time filter, and this would be a good place to do that if you already have the continuous aggregate created. So you can put a time filter here. This one specifically will make sure that to only return data that is older than newer than 3 months. Now you could also do this filtering on the Superset dashboard itself, or the dashboarding tool to use. That's fine as well. But what I found to be useful is that I try to do most of the things in the database. I'm trying to get the database to do most of the work because it will make sure that if there are any indexes or there are any things the database can optimize this way. Hopefully it will do all the optimization tasks, because with Superset there is a chance that Superset will, or other dashboarding tools will not use indexes, or will not take advantage of the different optimizations the database provides. So I'm going to create this view, and then we will jump back to the dashboard. So let's create this view. Done. Now going back to the Superset dashboard, again we need this view for the filter, so we don't have collection IDs as the filter. Instead, we want slug to be the filter because that's more meaningful and easier to use, more user friendly. So to do that, let's edit the chart, or it's a filter, so let's edit the filter. And now if we go here, I will probably need to refresh the data set inside Superset so it can update the metadata and all that. So let me edit data set columns and sync columns from source. So this, actually, I will need to use the view that we just created. So good thing I remembered. So again, the demo collections daily is the continuous aggregate, which has the same columns that the continuous aggregate has, which are these columns. So we didn't change that. We just created a new view on top of the continuous aggregate. So instead of using this, we need to add the view we just created for Superset as a new data set inside Superset. So we go again the same spiel that we did with the continuous aggregate. We try to find the view here in this dropdown. And here we go, demo collections daily view. So this is what we were looking for. Let's add this. And if we add this, we need to use this view for the filter. So the data set has been saved. All right, let's go back to the dashboard. And now if we edit the filter, we can change the data set to demo collections daily view, which is the view that has the column that we need. So we change the data set. Now, if we configure the filter, what you can see here is that we don't only have collection ID, we also have slug, which is a very useful thing. So I just choose slug instead of collection ID, and as a default value, I just define an actual existing collection. Maybe I define CryptoPunks. If I define CryptoPunks as the default value, the filter should work. So I just save it and I go to the dashboard. So let's see what happens here. So as you can see, we have CryptoPunks in the filter. And now what you see is the other chart did something very weird. So we have a lot of stuff going on in the other chart. And this is because this chart still uses the collection ID as a filter, but we didn't have any filter set because instead of the ID, we have the slug. So I'm actually quite surprised that my browser hasn't crashed because this is a lot of data. So that's a good thing. So let me try to edit this chart, and I'm trying to stop from loading because again, it's a lot of data points. Like again, it's going back, multiple months. We have I don't know, tens of thousands of collections, and it's just a lot of data points. So for one chart. So in the group by section, we still have collection ID, which is not correct. So let me change that. And let me use the we need to switch the data set that this chart uses. We need to change the data set to the view that we created, which is demo collections daily view, that is specifically created for Superset. So let's do that. Right now, I will need to make the same, configuration with the metrics. I choose. Now you can already see that we have slug here as a possible option, so it works properly. But the metric is still volume, so that's going to be volume. Let's call it again trading volume. And again, as aggregate function, just choose something that is not count or count distinct because the aggregation is already done by TimescaleDB. So I just go with max. Let's hit save. For time grain, let's stick with the original value, and that should be it. We don't set any filters here. The filters will be set on the actual dashboard. So I go save, and go to dashboard. And so now we're gonna have the default value in the place of the collection filter, which is CryptoPunks. And in the time series chart, now we have the trading volume of the CryptoPunks collection over time. And if I hover over the chart, we can see the actual data points. And also, if we want to make sure that this is actually for CryptoPunks, so the filter actually works, we can do so by going to the customize panel and show legend. that shows the trading volume. That's not what we need. Maybe not marker. Show value, no. Group by. I didn't set group by. Well, that's the problem. So we need to set a group by so it actually shows you what it tries to group by, which is slug. So if I set this value and I run the query, we will see that now we see CryptoPunks. So instead of trading volume, we see CryptoPunks, and which is the name of the collection, and the value and the trading volume of the collection on the given day. So this is what we wanted. So now let's go back to the dashboard and try some other filter. So this is for the collection CryptoPunks. Let's try another one. Maybe let's try 𝗥𝗲𝗃𝗁𝗃. So you can either choose one from the drop down, or you can just type it in. So I type in 𝗥𝗲𝗃𝗁𝗃. That should be a valid collection slug. So if I hit apply, the chart will get updated. As you can see, now it shows CryptoKitty's trading volume over time. And as you can see, as opposed to the first version of this dashboard, which included data going back to the beginning of this year, now because we applied the time filter here in the view which is used by the dashboard, we have a 3 months interval defined as a filter, so it only shows data from the past 3 months. So the chart is also showing data only from the past 3 months. So this is what we wanted. And one interesting thing that you could also do is combine two collections. So for example, CryptoKitties, and let's combine it with CryptoPunks. If I apply it, there will be two lines here. One for CryptoKitties and the other one is for CryptoPunks. So this is an example, and again, as you saw, it's fairly quick to apply the filter and see a chart for different collection, and you can also look at multiple collections, and this is all using TimescaleDB and continuous aggregates under the hood. All right, so that's what I wanted to show as far as dashboarding and how to use continuous aggregates to fuel dashboards. Now going back to my slides, now I will briefly talk about compression. And basically what we are going to try to do is compress the data that is used for the dashboard. So basically we will try to compress the data that fuels the dashboard. And why would you do that? You would do that in order to reduce storage costs. Maybe because you're trying to stay below a specific limit, you don't want to go over I don't know, 25 gigs, 50 gigs, or 100 gigs, or whatever your if you use a cloud provider, maybe use Timescale Cloud, you want to stay below a specific storage limit, which is absolutely fine. And you can use TimescaleDB compression to do that in a very efficient manner. So a little bit about compression. I'm not going to go super deep because we have again a lot of content regarding compression. Actually, my colleague Ryan Booz, who is director of developer advocacy at Timescale, he just recorded a stream or a video yesterday about compression, going super deep, how compression works under the hood. So I recommend watching the video on YouTube on the Timescale YouTube channel. So I'm just going to be brief. So compression is one of the cornerstone features of TimescaleDB. Compression and probably context aggregates are the two most used or useful features of TimescaleDB. On a high level, how it works. So compression basically in TimescaleDB converts multiple rows into one row based on one or multiple columns, which you can define when you enable compression. And you need to define these columns as segment by columns. But basically, whatever you use to segment by that column will not be compressed, but everything else will be. And let me go ahead. And what will happen is that TimescaleDB, instead of storing each data row in one row, it will store multiple rows data inside one row, and it will create an array from the data. So if you segment by, for example, if you're recording temperature values, and you have a column called device ID, and you have a column called the actual temperature in Fahrenheit or Celsius, and you define the device ID as the segment by column, that's not going to be compressed, but all the other the other column, the temperature values, will be compressed into one row per device ID, and the values will be stored in an array. And what ends up happening is that because you store less rows after compression, that means less disk space will be required, because less rows requires less disk space, and ultimately it will reduce your disk storage costs if you have any. And and that's what happens on a high level. Again, there's a lot of factors going into the whole compression process, and there are a lot of factors that can change the result of your compression. But I recommend checking out the recording that we have on the TimescaleDB YouTube channel, and also the TimescaleDB documentation about compression to learn more. All right, so in order to use compression, you need to enable it first. The way to enable it is alter table and the name of the table. In this example, it's called temperature. And then TimescaleDB compress. And you will need to define one or more segment by columns. The example that I mentioned, with the temperature values, you might want to define the device ID as the segment by column. And with this, you don't actually compress it yet. If you run this command, it will just enable compression. You will need to either manually compress it later, or set up a compression policy so it automatically gets compressed. Now you can also define another parameter when you enable compression, and this can be also very useful. This parameter can also very very useful. Depending on your data set, the values you have in your database. But this is the order by argument, compress order by. The default value of this is actually time descending, and basically what it does is that it will order the values in your compress table. And the reason it's important, because the the order of the values will affect how the actual compression algorithm will perform. And the your compression ratio at the end will be better if the values in your table either has some kind of a trend, like the values follow some trend, some trend line, or the values next to each other, in one row next to each other, they are close. So for example, if you have random values in one of your columns and you want to compress it, it will probably um, perform worse as far as compression ratio, uh, as opposed to um, if you have values that are very close to each other, they follow some kind of trend. um, but yeah, as I said, there's a lot of stuff that goes into this, and we have other content that went deep into compression. So I will put links in the description if you want to learn more about this topic and how to configure compression properly. Um, so we can move ahead with today's content. Um, and as I said, you can manually compress chunks, which we will do uh, today. And the way to do that is by using the compress chunk function. And compress chunk function will only compress one chunk. But if you want to compress multiple chunks, you can use, SQL code, something like this or similar to this. You can use the show chunks function, which will return a list of chunks from the specified table. In this case, the table is called temperature, and you can define two parameters. One is older than, and the other one is newer than. And so with this, you can define which chunks should be compressed. So in this example, all the chunks between chunks that are older than 1 week and newer than 3 weeks will be compressed. You can also set up a compression policy if you want to do this, continuously all the time. And so, for example, you can set a policy to compress data that is older than 60 days. And so, basically, you compress data that is older automatically, and so you don't need to, uh, spend time manually compressing it every time. All right. Oops, it's not over yet. Now we are going to demo um, uh, how compression works and how to set it up for the sample data set that I'm using now. So if I go further down, so again, as I showed in the other slide, this is how we enable compression. A segment by column is required to be, defined. You can also additionally add order by columns. And so first of all, I will try to enable compression using this SQL script, but this will show an error, and I will explain why. So if I try to run this, I just make sure that I use the correct table name, which is I believe that's the correct one. So I run this code, we will see an error which says that the column ID must be used for segmenting or ordering. And this is because on the table NFT sales demo 2, we have a column called ID, which is actually unique, and this needs to be used either as a segment by column or as an order by column. Also, there is one important thing with compression, which can be a limitation, but technically it actually makes sense why it's there. So if you have if you have any foreign keys in your table that you're trying to compress, you will need to specify those foreign keys, all the foreign key columns in the segment by argument, which can lead to results that you might not expect. Um, and so, for example, with this table, I decided to drop all the foreign keys. The only constraint I have is as the error shows, I have an ID column which is unique. Well, actually, it's there's a unique index on the ID and time. So that's the only constraint I have. With that constraint, um, to have a workaround around this, limitation, I can include the ID column as an order by column, which actually even technically makes sense because, as I said, the default value for order by is time descending, time being the column which stores the timestamp values in the table, and the ID column is actually it's regarding like trends and the values and how the values are relating to each other in the table. It's very similar to the time, because if the time as the time goes on, the time values are bigger and bigger and bigger, and also the ID value is bigger and bigger and bigger. So in practice, it doesn't make a difference whether I order by time or ID. It's going to be the same. So I just include the ID column as an order by column. And if I run this will actually work, hopefully. Yes. So with this, we enabled compression. But again, um, it's important that I decided to drop all the foreign keys from the table, which can be a problem in some use cases, or if you want to keep the foreign keys, you might want to configure the compression in a different way. So moving on, um, as I mentioned, the compression feature inside TimescaleDB will only compress one chunk at a time. So you will need to specify which chunks you want compressed. And so first of all, maybe let's have a look at all the chunks that we have in the hyper table, which we can do so using the show chunks function and then the name of the hyper table. So if we run this, see a bunch of chunk names, which is these are all TimescaleDB internal uh, chunks. There are actually tables. Now let's say, because as I mentioned, our goal here is to compress the data that is used for the dashboard. So if we go back to the dashboard, we want to compress data that is basically that can be visualized here, which is basically all the data from the past 3 months. Because if we go back to the definition of the well, not the definition of the continuous aggregate, but rather the view that Superset uses, this is it. So we define that we want to see data from the past 3 months. So that is displayed, or that can be displayed on the dashboard. So we want to compress that data from the past 3 months. So to do that, we need to find the chunks from the past 3 months. And again, we can use the show chunks with the newer than argument. Now, this is important to include, or important, but it's more like useful to include the name of the argument here, and not just do something like this. Because if you do this without an argument, the first parameter, the first optional parameter of show chunks is actually older than, not newer than. So you will see a very different result than you might expect. So I just include the name of the parameter every time. So I want to see chunks that are newer than 3 months. So if I run this, as you can see, we only see 10 chunks now, which are from the past 3 months. Now, if you're curious why we only see 10 chunks from the past 3 months, um, because you might think that I didn't change the default TimescaleDB interval for a chunk, which is 1 week, 7 days. So I didn't change that. Then I should see about 12 chunks, because 12 weeks equals 3 months, but we only see 10 chunks. So if you're curious why that is, I was curious, so that's why I looked it up. You can use this SQL script to learn more about a specific chunk, and basically this one uses the TimescaleDB information. One of those TimescaleDB information views called chunks, and I basically I'm just interested in the ranges in those chunks. So now we see um, all the chunks from the given hyper table from the past 3 months, and we also see the time range of a specific chunk. And we also see whether the chunk is compressed or not. This is useful because we are about to compress these chunks. So if you look up the ranges, what we can see here is that all the ranges are the range start and range end, they are 1 week apart, which is that's what we expect. But we only have 10 chunks, and the reason we only have 10 chunks is that if you actually look at um, the timestamps, we have a gap between 14th of October and 28th of October. We have a 2 week gap where we don't have data. um, Now, for now, we let's assume we don't know why that is. But, it can happen in any using a real world data set. But it's useful to be able to look up things like this using the TimescaleDB information views, so you are not surprised why there are 10 chunks in 3 months. Well, because there were 2 weeks when you had no data. All right, so now that we got it out of the way, let's compress these chunks, and we can do that manually using the compress chunk function. And what it will do, again, this is the same that I showed on the slide. First of all, we are going to use the show chunks function again to return chunks that are newer than 3 months. And then we are going to use these chunks and compress them one by one. And we also apply this parameter, which is, in this case, it's not needed. But what the if not compress true parameter will do is that it will only it will try to compress only those chunks that are actually not compressed. This can be useful if you are not sure whether the chunks have been compressed or not. You can submit this parameter to make sure that only those chunks will be compressed that are not yet compressed. All right, so if I run this will take probably about 10 to 15 or maybe 20 seconds to compress the 10 chunks. And I have another SQL script here which you can use to decompress these chunks that you already compressed. We are not going to do that now, but in some cases you might want to do that as well. So as this process is done, these chunks should be compressed. And how we can check that, we can run the same query that we ran before. And if you run this, again, it returns those 10 chunks. And now, if you look at the is compressed column, these are actually compressed. So it worked. Now, if you want to see the actual, compression ratio, you can also do that using the chunk compression stats um, um, function, which will return the the before and the after compression total bytes, and you can also use functions like pg size pretty, which will convert bytes to megabytes and gigabytes. And this query will return all the compressed chunks and the before and after sizes. So if I run this, uh, what we see is that again the same 10 chunks, and we see that uh, we were able to compress it, um, compress all the chunks. Like for example, the first one, instead of 61 megabytes, we have now 12, or instead of 122 megabytes, we now have 23. So this is pretty good. Now to see the ratios, this is because these are just the actual sizes. To see the total, compression ratio for all these chunks, let's try this next query, which uses the same query as we used previously as a subquery, and then sums them up and then calculates the ratio. So if you run this, see here is that those again, we didn't compress the whole data set, we just compressed the data from the past 3 months. But that past 3 months was 882 megabytes. After compression, it 174 megabytes, and that equals to about 80% compression. Which is not the best. Sometimes uh, TimescaleDB compression can achieve 90 or even 95% compression rates. So that's not unusual. But as I said, there are a lot of factors that go into the compression and how the compression algorithm will work. And also, I'm fairly positive that if I had spent more time configuring the compression on this data set, I would have been able to achieve a better compression ratio. But that's what we have for now, 80%. So now that we actually compress the data, the final thing I wanted to show, because I know we are a little bit over time, but the final thing I wanted to show is that if I go back to the dashboard, again, this is the same dashboard we were working on before, this should keep working, even though the underlying data is compressed. So if I just update all these, well, we just have one chart and the filter, but if I update the dashboard, which I can do here, refresh dashboard. So if I refresh the dashboard, it should work properly. And as you can see, there is, it's working okay. Let's try maybe another. Maybe just let's try the 𝗥𝗲𝗃𝗁𝘁 collection as a filter. So if I apply the filter, um, we have the same time chart as before. We have the same values as before. We have pretty much the same speed as before. So it's working properly. Let's try just CryptoPunks to see how it goes. So I apply the filter, the chart gets refreshed, and we have the same chart. So the important thing here is that the on the front end of the dashboard side, the dashboard is working. It's the same data, so there is nothing that changed on the dashboard. What changed is on the backend side of things, which is we have less data on the disk regarding size. Like we only have 20% of the data actually stored on the disk because of the compression. So again, this is just a very small sample of data, but if you were to scale up and have not this amount of data, but hundreds of gigabytes of data or terabytes of data, ideally you would be able to achieve a similar compression ratio, or probably even better compression ratio, if if you configure the compression feature properly. Also, your data set is, you know, if your data, the type of data you are working with, and the columns and the data types you are working with work well with the compression algorithm, then you would have, you would be able to basically save more, even more on the disk storage costs, which can be, it can be really useful if you wanna, save on that side. All right, so I hope it was useful. We did, quite a few different things. If you are interested to learn more about, TimescaleDB in general, or continuous aggregates, and other things Timescale related, I highly suggest checking out the Timescale documentation, docs.timescale.com. We also have a really, great community on Slack, slack.timescale.com. We have more than 7,000 members, full of TimescaleDB users and TimescaleDB team members. And you can also tweet us at TimescaleDB, or you can tweet me, 𝗥𝗲𝗹𝗲𝘃. And very important, we are hiring for a lot of different positions, but we are also looking for people in the developer advocacy team. So if you want to join, go to timescale.com/careers and join the team. So I hope this was useful. Again, if you're watching the recording, there are links in the description. And we will see you in our next stream. Bye.